We present semantic video CNNs through representation warping. In this work, we present a technique for converting image CNNs to video CNNs.
In recent years, ConvNets have significantly improved the performance of image segmentation. However, most video segmentation methods still process each frame independently, causing temporal inconsistencies. Here, we propose to adapt image CNNs to video CNNs using a warping module. We call this module NetWarp, and we use it to combine intermediate CNN representations of adjacent frames. A NetWarp module can be included at different depths. Multiple NetWarp modules can be used to form a video CNN. NetWarp modules add only a small computational overhead and are end-to-end trainable.
Now we present an overview of the proposed NetWarp module. The main design principle is to use optical flow of adjacent frames for warping intermediate network representations across time. First, we compute optical flow and intermediate CNN representations for 2 consecutive frames. The NetWarp module takes the optical flow as input and transforms the flow with a small CNN. Then the transformed flow is used to warp the intermediate representations of frame t-1. The previous frame's warped representations are then linearly combined with those of the current frame. The output is passed onto the remaining CNN layers for semantic segmentation. All these computations in the NetWarp module are backprobable, making the resulting video CNN end-to-end trainable.
Since NetWarp is generic, we use it to augment several existing state-of-the-art CNNs and observe improvements across all of them. Now we present results on the CamVid and the Cityscapes datasets.
Here we show quantitative results on the CamVid test dataset. Adding our NetWarp modules to the dilation CNN, we observe larger improvements across different metrics compared to recent CRF in information propagation techniques. Notice that the improvements come at a mere cost of 15 milliseconds on top of the baseline CNN. The runtime also includes the optical flow computation.
We observe similar improvements across 3 different metrics on the Cityscapes validation and test sets. With only few milliseconds overhead, we see improvements in both the single and the multi-scale versions.
We find that the NetWarp augmented PSPNet is on par with the current top-performing method. It outperforms current top models in terms of instance IOU by a significant margin of 1.4%.
We show some qualitative results from the Cityscapes validation dataset. Our method is able to recover thin structures like poles, traffic lights, and traffic signs accurately using temporal context.
Here we visualize transformed flow for some sample images. We can clearly observe that the structure of the scene is much more pronounced in the transformed flow, indicating that the traditionally computed flow might not be optimal for semantic segmentation.
This video shows semantic results on the Cityscapes demo video. Top left shows the input video. Top right shows the output of PSPNet. Bottom right shows the output of PSPNet augmented with the proposed NetWarp module. Bottom left shows pixels where the output of PSPNet and NetWarp PSPNet differ. It is clear that the NetWarp PSPNet mainly differs from PSPNet at object boundaries.